So today we will continue what we have learned in before the break. This is chapter 4. So in chapter 4, you have been introduced to latch and flip-flops already. The register, chief register, the counter, and today we will look at the finite state machine, or in short is FSM. And also we will look at what is called an ASM, or algorithmic state machine, which is actually a state machine also, but in the form of a flow chart. Yeah. So you should know already. Uh, you should know already what is the difference between the latch and the flip-flops, which where the difference is that latches for latch, the output is sensitive to the level of the clock. All right, means that whenever the clock is active, the output will change depend on the input. And the this is flip flop, the latch. So the one that we use in digital design is the D Latch. Yeah, where the output will equal to the input, or will follow the input when the clock is active, right, like this. So here is the time where the when the clock is active. So we can see that if d equal to 1 here at this time, until this time, so the output will follow the input. So here, because the clock is not active yet, so the output is still 0 because the previous input is 0. And then go to 1 here because this is 1. And until here, the clock is not active, but the not active. So it will the output will still remain the same until the next active clock level here. So it will go down to 0 because here is 0. So that is latch, and this is flip-flops, where the output is sensitive to the clock edge. So whether it is a positive edge triggered or negative edge triggered. So in this case, is the negative edge triggered. So the output is will follow the input whenever the clock edge here. So whenever the clock is from change from 1 to 0. So here we can see that we have 0 go to 1 because here d is equal to 1. Right? So this is a negative edge triggered. Yeah. So remember, flip-flops is sensitive to the edge only, right? But the latch sensitive to the level of the clock. And we also learn how to create the latch or memory circuit in the Verilog. So this is how, very easy, straightforward. And this is how we create the D latch, and this is how we create the D flip-flops. Yeah, where we use the post edge statement here, means that the clock is sensitive to the positive edge. If we use neg edge, means that the flip-flop is sensitive to the negative edge. We also learn what is blocking and non-blocking assignment, right? Where this one is called the blocking assignment, right? Where when we describe the sequential circuit, the flip-flops or the register, we need to be careful because when we use blocking assignment, right, we may end up with this circuit instead of this one, right? When we want to create the cascaded flip-flops like this, but if we write like this in Verilog using the blocking assignment, we will end up with this circuit, not this one, right? So to avoid that, we need to use what is called the non-blocking assignment like this, so that we can get the correct circuit. This is another example. So the rules is that when we want to design the sequential circuit, it is recommended to use the non-blocking assignment like this. But when we want to design the combinational logics, for example, the adder, the multiplexer, the decoder that we have learned in chapter 3, so it is recommended to use the blocking assignment here. And if we have n flip-flops or more than one flip-flops, like this, it is now called a register, and it is used to store an information, right? So for example, this is 4-bit register where we can store a 4-bit data or 4-bit information. Yeah, the information is come from this. This is the input, and we can get back the that data from the output of the of each flip-flops. So this is 4-bit, and we have learned also how to write the code, the Verilog code to describe the register, which is very easy. Actually, it is similar to the flip-flops. The only difference is that the size of the input and the size of the output. This is how we describe the register also, but now we can control the input, whether we want the input to enter the register or not, using the multiplexer. So for example, if load signal is 0 or not active, so the data from A will not go to the flip-flop. But when we activate this load signal or equal to 1, we now load the data A to the register, right? So this is the Verilog code to describe this. We have learned this, and this is another one where we have the reset signal here. So this is how to describe the register or flip-flops that we have a reset signal, and the reset must have post edge or next edge also, right? And it is actually an asynchronous reset or asynchronous signal. Asynchronous means that it is not actually not sensitive to the edge, but sensitive to the level, right, for the reset signal. So that means that whenever the reset is activated, the circuit or the data here, the flip-flop here, will always reset to 0. Means that the output here will always 0 if the reset is active. So to write the code for that is quite straightforward, where we have if reset equal to 1 in this case, post edge. So if reset equal to 1, the output Q is equal to 0. And if load equal to 1, in this case, if load equal to 1, so the output here is equal to A, the input. Means that this data will go to the flip-flops at the positive clock edge. So quite easy. But remember last time if we have if, so you need to have else. Yeah, so that is a requirement if we want to create the combinational circuit. But if we want to create the sequential circuit, so the Verilog compiler normally will automatically know this already, where if load equal to 0 means that the output Q will remain the same, yeah, will remain the same, or no change at Q. So in Verilog, no need to write that in the code. So this is another way to create the register, where now we use the parameter statement here, and this code is quite flexible, where we can change the size of the register by only change this and the number here, right? So for example, we want to change to 32-bit, we just change here to 32, and we have the 32-bit register, because we use this and this n now become 32 minus 1 is 31. 31 to 0 means that 32-bit. This is the shift load register, where we can load the data into the register and we can shift the data in the register, right? And it is shift from left to the right, yeah. And this is how we create. This is the same thing actually. This is how we create the flip-flops with multiplexer in front of that flip-flops. This one is the same one, but using this assign statement to create the flip-flop, to create the multiplexer. Right, this is how we define or describe this circuit using hierarchical design methodology. And this is how we design the same circuit using the behavioral modeling. And this is the more flexible n-bit shift register, where we can have n equal to 16, means that this is 16-bit. And this is another example of the flip-flop with enable input or load input is the same actually. And this is the counter, where we use to count number, right? So this is quite straightforward, where we can see that if reset, the output C is equal to 0, but if E equal to 1 in this case, means that the output here is C equal to C plus 1, right? So because we have the adder here, so this adder is plus 1 adder, increment plus 1. So if we want to have the counter with count every two steps, this is one step. So if we have two steps, we can plus 2. So we have count from 0 to 4, 6, and so on, right? This is another one where we can have the we can load any data into the counter, means that we can count from any number that we want. In this case, it will always count from 0. In this case, it can count from any number that we put here from this R, right? So because if load active means that we load the number to the register. So for example, if R equal to 5, means that we count from number 5 to the maximum number of the register. This is another example of the counter, where we can have one another signal to detect whether the number that we want to detect is detected or not, right? So for this example, we want to know whether the counter is full or not, means that if this one is 4-bit, so means that if all number is 1, yeah, this is 1, this is 1, this is 1, this is 1, means that TC equal to 1. So we can modify the circuit to have or to detect any number depend on what is the gate we have here, the combinational circuit we have here, right? So this is another kind of counter which is quite useful when we design the system, for example, to have the counter that count to a certain number, and we want to reset the counter back to 0 when we have reached that number. We also learn how to create the memory circuit, where this is the an example of memory circuit. This is 1K memory, 1 kilobyte. Yeah, 1 kilobyte, when one location here is 1 byte or 8 bit here. So we have 1204 location, starting from 0 to 1023, means that we have 1024 byte here. So this is 1K. So to declare the memory is very easy, where we can use rack. Yes, the size of the memory, which is 8-bit here, and the memory name, right? In this case, the name is MEM. So starting from location number 0 to location number 1023, or sometimes we call the address. This is the address 0, address 1, 2 until address 1023, and it is unique. So for example, if our data is stored here, so when we want to get the data from this, means that we access the location, we need to access the location number 3. So that is how we create the memory. So for example, in this case, we want to store the data or write the data into the memory. So data here must be the 8-bit data, right? Because our memory is 8-bit. So the data, for example, we want to write this data into the memory location 21. So this is the Verilog syntax that we can use to get or to write the data to location 21. And if we want to read now from location 250, for example, this is how. So the data is now our variable. So we can read to the variable here. Right? And this is how we initialize any bit in this, because we have 8-bit. So for example, in memory location 100 or address 100, bit number 0, we want to change only 1 bit in that location. So this is how. So this is memory address 100, and bit number 0 we set to 0 or we set to 1, depend on what we want to do. So it will automatically set or clear the bit 0 of memory location 100 to 0. So if we change this to 2, means that we want to change bit number 2 into 0. And this is how we create the memory, this memory. Right. So this is the definition, and this is data out is the wire here, right, where it is assigned to memory this and the address. So if the address here is this is 10-bit, if the address is 0 in this, so means that we get the data from location number 0 or address 0 to data out. And if this one is we want to write, this one is we want to write. So to write, we have one signal here. We call it the write enable signal, WE. So if write enable equal to 1, then we can write the data into the memory. So if we write like this, means that our read can always read anytime, or what we call the asynchronous read, right? Because this will not depend on the clock, so we can read anytime. But this one is depend on the clock. we can only write at the positive edge clock, and also we need to wait for this signal to be activated, then we can write to the memory. Okay, so that will be the story of the last lecture. So the video is not available yet in the in YouTube, so I will upload by maybe this week, so you can refer back to the video, right? Also, if we have time later on in the tutorial, we will try to write the code for this in quarters and try to simulate and see what happened to when we want to write data into memory, or we want to read the data into memory. Okay, so any question regarding this? Yeah, before we go to the next. Yeah. So any question?
So far, no, sir.
No, yeah. Okay.
Yeah.
So if no question, we will go to the next subtopic. This is the finite state machine. So now we will look at the more advanced sequential circuit, where it is very useful and very important in digital system. Before this, in chapter 3, we have learned that we have the combinational circuit, that the the output is only depend on the input, right? Means that whenever the input change, one of the input change, the output will automatically change, depend on the specification of the circuit, right? So for example, an OR gate, two input OR gate or two input AND gate. So whenever one of the input change, so it will immediately affect the output. So that is a combinational circuit. For the sequential circuit, we know that the output is not only depend on the input. So whenever the input change, the output change or not change is depend on the input, and also the past the past output or the memory of the circuit. So that characteristic or that behavior is very important when we want to design the circuit that that the output will need to uh, change, or we need to look at what is the input that coming, and also what is the previous output. So for example, we have something like this. All right, let's look at this example. Consider an application where the speed of an automatically controlled vehicle has to be regulated as follows. The vehicle is designed to run at some predetermined speed, means that the vehicle is run at the constant speed. Yeah, it's designed to run at constant speed. However, due to some operational conditions, the speed may exceed the desirable limit, in which case the vehicle has to be slowed down. Okay, so sometimes the vehicles can be uh, can run or can exceed the speed limit. So we want to have the mechanism to automatically uh, regulate the speed so that it's back to the normal speed, right? So to do that, we need to have the sensor that measure the speed, right? So that sensor, for example, we name it as W, right? So to determine when such action is needed, the speed is measured at regular interval. So we measure the speed at regular interval, for example, every 5 seconds, every 10 seconds, right? So let's a binary signal W indicate whether the speed exceeds the required limit or not, such that W equal to 0 means that the speed is within the acceptable range, and W equal to 1 indicate excessive speed. So it means that uh, when we measure the speed at the interval measurement, for example, time, 1 second, 2 second, 3 second, 4. So if at 1 second W equal to 0 means that the speed is okay, and another second if W equal to 0 means that the speed is still okay. But if W equal to 1 means that the speed is exceeding the desired speed. So what we want to do here is we will not slow down the vehicle yet, yeah, because if only one measurement, for example, the next measurement is going down to normal speed already, so it's then no need to slow down the vehicle, right? Because at the next measurement it's go down to 0 again already. So that should be okay. Means that this is maybe it uh, go up. The speed is go up for very short period. Then should be okay. But what if the next measurement and still W equal to 1? All right, means that this one is something wrong already, because uh, one measurement, second measurement is still exceeding the speed limit. So we need to do something to slow down the vehicle. So let's, for example, to slow down with the vehicle, we have another signal, yeah, which is named Z, to activate the mechanism to slow the vehicle down. So when the speed limit is still 0, so we still Z should be equal to 0. So here Z should be equal to 0, Z should be equal to 0, right? Because here only one time, so Z should be equal to 0. Here should be equal to 0. The fifth measurement, Z should be still equal to 0, because only one uh, measurement we have, yes, exceeding the speed, but only one measurement. But the next measurement is still exceeding the speed. So now we need to have Z equal to 1, so that our vehicle will be slowed down, right? So that is the thing that we want to do. So let's read this. The desired control strategy is that if the W equal to 1 during 2 or more consecutive measurement, yes, exactly this one, a control signal Z must be asserted to cause the vehicle to slow down. Thus, Z equal to 0 allow the current speed to be maintained, while Z equal to 1 reduces the speed. Yes, exactly this, yeah. So this is the specification, the system that we want to design. But when we look at this, yeah, uh, by using the combinational circuit, it is quite difficult, right? to design the circuit that has this behavior where if W equal to 1 here, because we have only one input, see, one input, W equal to 0, W equal to 0, W equal to 1, one time, Z equal to 0. The next equal to 0, it's still equal to 0. But if we have W 2 times here, now Z equal to 1. So how to do that? Using the combinational circuit, which is quite difficult because our circuit need to has some kind of memory, right? It must know what is the previous value of the input here, or previous value of the circuit. So for here, if it need to check whether the previous one is equal to 0 or not, or equal to 1. If equal to 0, the output here it's still 0. But the next measurement here, for example, the previous one is 1 already, and this measurement W is still equal to 1. So Z is now equal to 1. So that is uh, the problem, the engineering problem that uh, that we need to solve, and to use digital circuit to do this. We need a circuit that can that has a memory, which is the sequential circuit, right? So that is why uh, we 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 use sequential circuit to design this kind of uh, circuit. All right. So this is the general structure of the finite state machine, right? So we will use what is called the finite state machine to solve or to design the system that can do this. Yeah. So this is the general structure of the finite state machine, where we have flip-flops here, okay, or register, depend. So if we have only one flip-flop, so it is a flip-flops. If we have more than one flip-flops, so it is a register. And the output of these flip-flops will be the input of the combinational circuit here, or we call that as the output logic. And the input to the flip-flop here is from another combinational circuit here. And this combinational circuit is where the input coming, right? In our case is W, and the output here in our case is Z. And we have the clock. Of course, our flip-flop need to be triggered by the clock. And we have one feedback signal here, right, from the output here to be input to this combinational circuit. And this part of combinational circuit we call the next state logic. And we have also one wire here which is connected this connecting this input to the input of this combinational circuit, but the color is different here, means that it's uh, is spatial, right? So this is actually for the another kind of FSM. So we will see later the FSM. We have two type of FSM, which is called the more state finite state machine, more type finite state machine, and another one is called the milli type finite state machine. And the one without this line, this wire, is actually the more type finite state machine, and the one with this wire is actually the milli type finite state machine. We will see what is the difference between the two, and of course from the structure we can see already here the difference is that the more type we have only this line, but for milli type we have, yeah, we also have this line and also this additional line. In uh, in theory we can see that for the more finite state machine, if we don't have this, means that the output logic is only depend on the state or the output of the flip-flops, right? So let's remove this line if we don't have, yeah, if we don't have this line, meaning that the output here, the combination circuit here, the Z here will only depend on this wire. But if we have this line, now this circuit, this combinational circuit is depend on this input, the output from the flip-flop, and also depend on the input here, right? So that is the theory of what is the difference between milli type and the more type state machine. Now let's look at the first one, which is the more type state machine. So to understand better what is more type state machine, so the best way is to use this example to explain how it's designed, how to design this more type finite state machine and how it works. But before that, I think I need to share the update version of the lecture note. I forgot to share with you because I update uh, some information and some correction to the previous one. So let's share that first before we can go further. So I share in the Telegram group, yeah. So you can download from Telegram. Okay, so you can get the latest update of the lecture note for this chapter from Telegram. So please use the latest one, yeah, this one, because I have changed some of the signal name, like for example here, yeah, the previous one is using the Y2 and Y1, but I changed to Y1 and Y0. Okay, let's go back to the example. So again, we want to detect, yeah, or we want to regulate the speed of the vehicle such that it's within the allowed speed limit, yeah. So the input is this, the input to the controller, to our finite state machine is W, where W is actually the output from the sensor, yeah, where it sends the speed of the vehicle. So if the speed is more than the desired speed, so it will be 1. If below the speed limit, it will be 0. So for example here, if 0, so means that the output Z, the signal that will regulate the speed, we slow down the speed. So 1 means that it need to slow down, 0 is maintain the speed. So because 0, so maintain the speed. Here W equal to 1 here, but still 0 because only one time the speed is exceeding the limit, and the next measurement the speed is go down already, so of course 0. And 1 and 1 and for more type, yeah, actually it is it is the Z is delay for one cycle, yeah, one clock cycle. So it is actually going to uh, one cycle delay, right? So it is not one here, but it is one here, right? So for example here also the same. So actually the output is it here is not 0 yet, but don't care because we don't know yet the previous value of W what. So is the output is actually this one. So this and we can see that here still 0, but the next measurement if still 1, it is 1 to slow down the vehicle, and the next measurement if it is still 1, so we need to slow down the vehicle again until we have speed 0 here, and now that is 0 to maintain the speed after we go down already, because here the speed is okay already, then we maintain the speed here. So that's what we want to do. So uh, to do that, we need to create what is called the uh, what is called the state diagram. Yeah. So how to create the state diagram? So state diagram is our planning. Yeah, it's like the flow of the event that uh, we want to simulate. Yeah. So in this case, let's have a new one. So we want to create what is called the state diagram. So to create the state diagram, we can start with a circle, right, to represent the state. And for example, we name this state as state A, right? So why is it state? Because the output of the sequential circuit or finite state machine normally represented or called a state of the uh, uh, sequential circuit or state of the finite state machine, right? And the number of state is finite, and that's why we call finite state machine, right? The number of state must be finite, not infinite. So the first state is A, and at state A, the output should be 0. So here we say that at state A, the output is 0. And to change the state, it will depend on the input that coming to the finite state machine. So the input is represented by the arrow in a finite state machine. And of course, it depends on the uh, on the clock. Yeah, means that if you have two state, for example, you have another state here, you want to change from this state to another state, so it will change at the clock edge. Yeah, depend on the clock edge. So here, if for example, if the input W is equal to 0, so we should actually remain at state A, right? Because at state A, Z should be equal to 0. So whenever W is equal to 0, or every time, every measurement, if W is equal to 0, so we should stay at state A, and Z should be always 0, right? Because if we have the sequence like this, always 0 means that the speed uh, is constant, is less than the speed limit. So the Z should be, remember, should be always 0. But what if here Z equal to 1? Should we stay at state A? No, because whenever W equal to 0, we stay at state A. So when W equal to 1, we should go to other state, because if we stay at state A, yeah, for example, if W equal to 0 and W equal to 1, we stay at A. All right, and because we have only one input, if we have this, means that we will never go to other state, and we'll only have one state, and Z will always equal to 0, which is wrong. So what we want to do is we need to have another state. We can call state B, and at B, Z should be still equal to 0, because when we go from A to B, because of W equal to 1, and if only one here, W equal to 1 for one measurement, so Z should be still 0, right? So we should have another state, maybe here, where if another W come, we have state C, where Z now equal to 1. Means that here, if W equal to 0, we stay here 0, 0, 0, 0, 0. But if we have W equal to 1 for one measurement and W equal to 1 for another measurement, so we have Z equal to 1. So we should have this state, right? Now the question is that here, state B, when W equal to 1, yes, we go to C. What if W equal to 0? Whether we want to stay at here, or we go to other state, or we go back to state A. So it depends on what we want. So in this case, we need to check if W equal to 0, whether correct or not. So let's see, if W equal to 0, we stay here. So what happened is that, for example, the sequence is like this: 0, 1, 0, 1, 1, 0, 0. So Z should be, if 0, still 0. If 1, yeah, if 0, so uh, we stay at state A, yeah, the next cycle, because Z W equals to 0, right? We stay at A, and when 1, we will go to B, and Z should be equal to 0. And when 0 come here, if we stay at B, So let's say we stay at B. So we stay at B. So of course 0. And now 1 come. 1 come, we need to go to C. And the output is 1 already. All right. Which is wrong because only one measurement and we go to C already. Means that we cannot stay at B when W equal to 0 in this case. So we cannot do that. Now let's see if we go back to A. If we go back to A, what happened is that, so let's have this. This is still okay. And 0, 1, we 1. Yeah, we are at B now. And if 0 come, we go back to A. 0 come, we go back to A. And of course, we have 0. And when 1 come, we need to go back to go to B. And the output Z is still 0. And another 1 come, this one. So we go to C and the output is 1. This seems looks like correct, right? Correct. 1, 1, we have 1. And we go to C. So should be good. So we need to go back to A from here if W equal to 0. Now at C, if W equal to 1, we should stay here because remember, if we have 1, 1, another 1, so Z should be always equal to 1, equal to 1, equal to 1, right? So if we are at C and the next measurement is still 1, means that still exceeding the speed, so we need to stay here until W equal to 0, then we should go back to A. Because if 0, we need to wait for the another 1 to come, right? So this should be the state diagram of uh, our finite state machine to be designed. So from that, this is the this is just the flow of signal or flow of event in order to achieve the specification. So this is not the circuit yet. So we need to create or to design the circuit, the digital circuit, in order to behave like this. Right? So how to do that? So we need to use the sequential circuit, which is the flip-flops. So we need to have this is state diagram. We need to have what is called the state table, where we tabulate this to in the form of table instead of a diagram like this. So we create a table for that. So the table should looks like this. where we'll have here, we call it the this column, we call it the present state. This is the next state. This one is the output, and the output is actually Z. And we have, for next state, we will have two condition, where if W equal to 0, what is the next state? And if W equal to 1, what is the next state? So we need to extract the information from this state diagram in order to fill in the state table here. So the present state, the first one will be the state A. So this is the state A. And if state A, the next state will be whether B or A, right? B or A. It depends on W, whether W equal to 0 or W equal to 1. So if W equal to 0, the next state, when we have, or when we are in A, the next state will be still A. But if W equal to 1, the next state will be equal to B. And the output for state A is 0. So it should be 0. Next is B. When we are in B, so the present state is B, and the next state when W equal to 0 is state A. So we have A. And if W equal to 1, we need to go to C. So in this case, it's C. And at B, Z should be equal to 0. And we have the last one, which is C. And here, if W is 0, we need to go to A. And if W equal to 1, we need to stay at C or go to C. And at C, Z equal to 1. So Z equal to 1 in this case. So this is our state table. And this state table is useful, but we cannot create this circuit yet using this state table. We need to represent this in number, in digital number first, in order to create this circuit. All right, ABC is not a digital number, so we need to change this to, or represent this to digital representation, right? So we need to have another kind of table. So let's name this table as state assign table, right? Where we have this. We still have present state. Here we also have next state, and we have output here. But now, instead of using ABC, now we need to represent this ABC with binary number. So we have how many state here? We have 1, 2, 3 states. So to have to represent 3 different state, we need to have 2-bit number, right? Because if we use 1 bit, we can only have two values, which is 0 or 1 or 0. All right, so this is not enough. So we need to have 2-bit, where we can have 0, 0, 0, 1, 1, 0, and we can have until 1, 1. So in this case, 1, 1 is not used because we have 3 enough to represent A, B, C. So for example, A will change from A to 0, 0, or 0, 0 to represent A, 0, 1 to represent B, 1, 0 to represent C. And let's name this signal as, or this signal as Y1, Y0, and of course here is we have W equal to 0, W equal to 1, and here because this is A, so should be 0, 0, and here also A should be 0, 0, here also A should be 0, 0. Now B should be 0, 1, C should be 1, 0, 1, 0 for C, and let's name this as capital Y1, this is capital Y0, this also capital Y1, this one is capital Y0, this one is capital Y1, this one is capital Y0, this one is same. Okay, and output here is Z. Yes, we have 0, 0, 1, and because now we use the digital set value, and if we use 2-bit here, we need also to have all the possible combination, which is 1, 1. The last one should be 1, 1, but this one is actually don't care because we don't have any state for this. Yeah, if 1, 1, so we don't care, but we need to have this in order to design the circuit. All right, so now we have the state assigned table, and if we look at the state assigned table, it is in the form of like the truth table, right? Because when we look at our here the general form of the finite state machine, we can see that we have the flip-flops, we have the combinational circuit here, we have the combinational circuit D circuit here. So we can draw our circuit now to be something like this. So because we have 2-bit here, so we need to have 2 flip-flops. So when we draw, we should have 2 flip-flops, where this is Q, this is D, this is Q, and for example, this is a positive H. We have another one, 2 flip-flops, and we should have the combinational circuit here. We call it the output logic, and we have the input from here, And the output from here, of course, is Z. And here should be this. Yeah, this is actually the present state signal, which is Y1. Yeah, these two signal, which is Y1 and Y0. And we have another one. Yeah, remember it is always based on this, where we have flip-flop in the middle, the output logic and the next state logic here. So this here is called the next state logic. Where we have here, and next state logic is actually this. Right? Capital Y1 and Y0 is the output. So this is Y1, this is Y0, and the input for this is actually W. Yeah, because here the value here is depend on W, right? And also depend on this. Yeah, the value here is depend on W and also depend on this. And remember that we have this feedback signal. And this feedback signal is actually here. So we have the feedback signal, this, and also this one. And we have Y0, Y1 here, Y0, Y1 exactly represent this, because here this two signal Y1 and Y0 is depend on W0, W, and also this small y1 and y0, small y1 and y0, right? So our circuit should looks like this. Our final circuit should looks like this, but we need to design what is this logic. All right, means that the 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 logic that inside this box, where if the input is this and the output is this, and also this logic where the input is this, and the output is this. So to do that, this is quite straightforward, because we have this. So we can determine one by one. So for example, we determine this signal first. Yeah, create the circuit to get this signal first. So for example, let's create this first. So we need this. So we try to create capital Y1 first, means that this one, we want to get this one first, means that this one, and the input is this. Yeah, we want to get this one or this one, and the input is of course this two and also W. So we can have the K-map where we can have y1, y0, and w here 0, 1, 0, 0, 0, 1, 1, 1, and 1, 0. So quite straightforward. If w equal to 0, so we have 0, 0, 0, and don't care. So 0, 0, 0, and don't care here. And if w equal to 1, here we have 0, 1, 1, don't care. So 0, 1, 1, don't care. So that is our K-map. And from the K-map we can map or get the logic equation. So here we can map here because here is don't care. We can map to minimize our equation later on. And also this one we can map like this, such that the first term is, of course, we have this. So W, and here look at this. All right. So because this one is changed from 0 to 1 and this one is unchanged, so it should be y0. And for this, still W. And here should be this one, which is y1. So definitely we will have y1 or equal to W y0 plus y1. So we get already the logic for here, which is this. Next, we want to define this. Which is y0. So y0 is the same here. Y0 is depend on y1 and y0 here, and also w. So we need another K-map, y0. And we have this. And this is y1, y0, w, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And look at this, y0, yeah. So 0, 0, when w equals 0, this line. So y0 is 0, 0, 0, don't care. 0, 0, 0, don't care. And we have here another y0, which is 1, 0, 0, don't care. So it should be 1, 0, 0, don't care. And to map this, should be here only. Sorry. So this don't care is not here. 0, 0, 0, don't care. Right? So to map this is only this. Means that y0 is equal to, this one is w, and only this one. So we have y1 bar, y0 bar for y0. So we have y0 here already. Should be okay. And the last one is z. So the Z signal is actually easy. We can observe this. Yeah, see, because this is don't care. Actually, we can map together here, and we can see that Z is actually equal to Y1. See, 0, 0, 0, 0, 1, 1, and this is don't care. We can set to 1. So 0, 0, 1, 1. So it is actually Y1. So we can say that Z is actually equal to Y1. Or you can, if you're not confident of doing this, you can derive using the truth table also. So you can have truth table where the input of this is only two signal, Y1 and Y0 for Z. So you have Y0, Y1. Okay, so you have 0, 1 and 0, 1. So 0, 0 is 0 and 0, 1. 0, 1 is 0. 1, 0 is 1. And last one is 1, 1 is 1. So here, if we map this, we have this, and this is exactly Z equal to this Y1. Right? So now we have all the equation. We have Z, we have capital Y1, we have capital Y0. So now we can create the circuit. Right? We have all of this. Now we can create the circuit. So the circuit for Y1 is this W, Y1 plus or Y0. So this is W, this is Y1 or Y0. So we have Y1, and Z is, this is wrong, Z is Y1, right? So Z is Y1. So in your note, need to update again, where Z is now Y1. Yeah, based on our equation, Z is Y1. Right? So Z is Y1. And we have Y0. Y0 is W. Y1 bar, this is Y1 bar, which is from Q1, Y1 bar. And we have Y0 bar, which is this Y0 bar, and we have Y0. And of course, we have the clock, and we have the reset here. So now this is the circuit to solve this problem, or to the circuit for this specification. All right, to get the output or to behave like this. Okay, so now is almost 4. So we will have 5 minutes break, and come back. We will see how to describe the FSM using Verilog program or Verilog code.